Welcome back. Our previous video introduced the basics of learning models and noisy signals, and the idea that beliefs might be updated gradually over time as signals accumulate. And in this video, I wanted to compare and contrast learning models with the factor models that we've covered previously. At first glance, these might appear to be related frameworks that compete for the same type of problem. Both have composite error terms, and both are trying to get information out of measurements that are measured with error, either formal measurements in a measurement system or a sequence of signals that are noisy. But in actuality, each is built on very different assumptions about what agents know and when they know it. So let's break down some of the key similarities and differences in these two approaches. If you recall from factor models, we had a set of noisy measurements, which we indexed each measurement by m sub j. And in learning models, we have a sequence of signals, which we index by s sub it. And in factor models, what we're trying to do is use common correlation among the m sub j's to infer what the underlying low-dimensional factor is, and separating that from measurement error. And in learning models, we're doing something kind of similar. We have a sequence of signals that we're receiving over time, and naturally, correlation over time in those signals is going to uncover the underlying value of a sub I that we're trying to learn about. Both models have a composite error and can be written equivalently as a sub I plus epsilon ij, or in learning models, this would more formally be epsilon it, just to emphasize that this is over time and this is potentially cross-sectional over different measurements. But of course, we can just redefine indices of variables however we want. The key difference between these two models is that the factor AI is known to the individual in factor models, but the information AI is unknown to the individual in learning models. And in both models, the researcher does not know the true value of AI. And then another critical feature, which I've already touched on a little bit, is that in factor models, we could, as long as we have enough measurements, we could have a cross-sectional model, and we wouldn't need anything repeated over time. As we talked about toward the end of that factor model mini-series, there are situations where we can think of repeated measurements over time as being additional measurements in the measurement system. But in learning models, we have to have the time element because the individual can't get multiple signals simultaneously. So learning models have to use panel data. Factor models we could do in cross-sectional or panel data. And then related to the idea of what's known to the individual, in factor models, the individuals have private information relative to the researcher. But in learning models, they lack this information initially and slowly learn about it over time. Once we put this all together, we can understand that these two approaches are complementary and not substitutable. And later on in the mini-series, as we go through some modern empirical economics papers that have used these approaches, we'll make that more clear. I hope you found this comparison helpful in trying to understand the pros and cons of each of these types of models. And in the next video, we'll press forward on learning models and talk about the concept of Bayesian updating. This is the foundation through which agents rationally process signals and revise their beliefs over time. And in particular, we'll see that if we assume that agents are Bayesian updaters, that makes the formulas for their beliefs at any point in time very simple and clear. So I hope to see you in that video.